Hello learners, I am Dr. R.B. Malati, Assistant Professor, Chhattisgarh Swami Vivekanand Technical University, Bhilai. I welcome you all again to the course Essentials of Surveying Application and Techniques. In the last class, we studied the tachymetric distance equation D is equal to Ks plus C and also discussed how to determine the constants K and C using the staff intercepts on level ground. Yes, today we will learn how to determine the distance and elevation for inclined sides for two cases, that staff held vertical and staff held normal. We will also explore the different type of telescopes used in stadia theodolites and determine the tachymetric constants. I will also try to give an overview of analytic lenses in tachymetry today. So, let us start with the determination of distance and elevation formula for inclined sides with staff held vertical first. There are two figures shown for you, one at the angle of elevation and another at the angle of depression. Let us understand the setup first. Imagine you are using a theodolite or a similar surveying instrument. The instrument's line of sight OC is aimed at a vertical staff. The staff intercept AB is a portion of the staff between the upper and the lower stadia heads of the instrument. Since the staff is vertical and the line of sight is inclined, the intercept AB is not perpendicular to the line of sight OC, which is clearly seen in the figure. To make sense of the setup, we draw an imaginary line A dash B dash perpendicular to OC passing through the point C, where the central line of sight intersects the staff. Let's also define some key angles. Theta is the angle of elevation if OC is inclined upwards, or it is an angle of depression if OC is inclined downwards. And alpha is the angle suspended by the stadia head at the instrument. We can use trigonometry to relate these angles, understand how staff intercept AB relates to the distance OC. So, at point C, the angle between OC and the vertical line CF is 90 degree minus theta. It's clearly shown in the figure. The angle BCB dash is theta, and similarly A dash CA is also theta because A dash B dash is perpendicular to OC. At point C, the angle between OC and the vertical line CF is 90 degree minus theta. The angle BCB dash is theta, and similarly angle A dash CA is theta because A dash B dash is perpendicular to OC. The small angle suspended by the stadia head COA dash is alpha by 2. Here we assume the angle alpha is very small. The angle CA dash O is approximately 90 degree minus alpha by 2 because angle COA dash is also small. Let us simplify the angles. Since angle CA dash O is very close to 90 degree, we approximate CA dash A angle as 90 degree plus alpha by 2. Since alpha is small, we can further simplify it by saying angle CA dash A is 90 degree itself. Now calculating the intercept A dash B dash. The intercept A dash B dash is the projection of the actual staff intercept AB onto the line A dash B dash, which is perpendicular to the line of sight OC. We can express A dash B dash as a sum of the projections of AC and BC. So, A dash B dash is equal to A dash C plus B dash C. And by using the basic trigonometry, we can write A dash C as AC into cos theta. Similarly, we can also write B dash C as BC into cos theta. Therefore, the total intercept will now become A dash B dash is equal to AC plus BC into cos theta, which is equal to S into cos theta. Here S is the actual intercept AB onto the staff. Now determining the inclined distance OC. The inclined distance OC is the distance along the line of sight from the instrument to the staff. So, using the intercept A dash B dash, the inclined distance can be calculated as L is equal to K into A dash B dash plus C. Here K is a constant related to the instrument's property and C is another constant often related to the instrument setup only, like the focal length of the lens. Now, substituting the value of A dash B dash into this formula, we get L is equal to K into S into cos theta plus C. I hope it is easy for you to understand. Now, let us determine the horizontal distance capital D. The horizontal distance capital D is a projection of the inclined distance L onto the horizontal plane. That is what we often need in surveying actually. So, D is equal to L into cos theta. Substituting the value of L, we get D is equal to K into S into cos theta plus C into cos theta. And expanding this gives us D is equal to K into S into cos square theta plus C into cos theta. This formula gives the horizontal distance from the instrument to the staff considering the inclination. Now, let us determine the vertical distance or elevation denoted by V. The vertical distance V is a difference in the height between the instrument and the point on the staff being sighted, and it is influenced by the angle of elevation or depression. So, we can write V is equal to L into sin theta. Now, you know the value of L. So, substituting the value of L, we get V is equal to K into S cos theta plus C into sin theta. Now, expanding this, we get V is equal to K S cos theta sin theta plus C sin theta. Using the trigonometric identity formula, sin 2 theta is equal to 2 times sin theta times cos theta. This V can be rewritten as V is equal to half into K S sin 2 theta plus C sin theta. Finally, let us calculate the elevation. So, to calculate the elevation of the point onto the staff to the height of the instrument, we have these equations. For the angle of elevation, theta above the horizontal, elevation is equal to height of the instrument plus V minus h. For the angle of depression, theta below the horizontal, the elevation is equal to hi minus V minus h. So, here hi is the height of the instrument above the ground and small h is the central hair reading on the staff. So, summarizing all the formulas, the inclined distance L is equal to Ks plus C and horizontal distance D is equal to Ks cos square theta plus C cos theta, and the vertical distance V is equal to half Ks sin 2 theta plus C sin theta, and elevation of the staff station for the angle of elevation is hi plus V minus h, and elevation of the staff station for angle of depression is equal to hi minus V minus h. Hope you got a clear understanding of this derivation. Now, moving to the next case, that is when the staff is normal. Let us understand the setup here. Imagine you are using a surveying instrument and your line of sight OC is inclined either upward or downward. The staff intercept AB is a section between the upper and the lower stadia head, and intercept AB is normal to the line of sight OC due to the inclined view. An imaginary line E dash F dash is drawn normal to OC. And we need to calculate the inclined distance capital L, the horizontal distance capital D, and the elevation of the staff station. So, let us understand the variables in setting up the instrument. S is the staff intercept, which is denoted by AB, and H is the central hair reading on the staff, denoted by CE. Theta is the angle of the elevation if the line of sight is inclined upward, or angle of depression if the line of sight is inclined downward. L is the inclined distance OC from the instrument to the staff, and capital D is the horizontal distance OF dash from the instrument to the point on the staff. Now calculating the inclined distance capital L. The inclined distance L is the straight line distance from the instrument to the staff measured along the line of sight. The formula for the L when the staff is held normal to the line of sight is given as L is equal to capital K into S plus capital C, where capital K is a constant related to the instrument and capital C is another constant often associated with the instrument setup, like the focal length of the lenses. So, now let us calculate the horizontal distance capital D for the angle of elevation. So, capital D is equal to D of OF dash plus D of F dash F. To find the horizontal distance D of OF dash, let us project the inclined distance L onto the horizontal plane. This is simply done by multiplying L by the cosine of the angle of elevation theta, isn't it? So, capital D is equal to L into cos theta. Substituting the value of L, we get capital D is equal to Ks plus C into cos theta. Now, consider the vertical component due to the central hair reading small h. The projection of the reading onto the horizontal plane is F dash F is equal to h into sin theta. So, now the horizontal distance capital D will become D is equal to OF dash plus F dash F. So, substituting all the values into this equation, we get D is equal to Ks plus C into cos theta plus h into sin theta. Let us now determine the horizontal D for the angle of depression. When the line of sight is inclined downward, the process is similar but with a slight change in the sign. So, capital D is equal to DOF dash minus DF dash F. OF dash is equal to Ks plus C into cos theta and F dash F is equal to h into sin theta. So, the horizontal distance D will become D is equal to Ks plus C into cos theta minus h sin theta. Now, the vertical distance F dash C denoted by V. This is the difference in the height between the instrument and the point on the staff influenced by the angle of elevation or depression. So, V will become F dash into C, which is equal to L sin theta. You know the formula for sin theta, which is equal to V by L. So, from there we have obtained this equation. Substituting the value of L here now, we get V is equal to Ks plus C into sin theta. Now, The elevation of the staff station when the line of sight is inclined upward is given as elevation is height of the instrument plus V minus h cos theta, where V is a vertical distance component calculated previously as V is equal to Ks plus C into sin theta. And the elevation of staff station when the line of sight is inclined downward will be elevation is equal to height of the instrument minus V minus h cos theta. Here V is a vertical distance component which was calculated earlier, and it is equal to V is equal to Ks plus C into sin theta. Summarizing all the formulas, that is summarizing the formulas that has been done for the distance and elevation for inclined sight are for inclined distance L is equal to Ks plus C, and the horizontal distance D for angle of elevation D is equal to Ks plus C into cos theta plus h sin theta, and the horizontal distance D for angle of depression D is equal to Ks plus C into cos theta minus h sin theta, and the elevation of the staff for angle of elevation is equal to hi plus Ks plus C into sin theta minus h cos theta. Elevation for angle of depression is given as hi minus Ks plus C into sin theta minus h cos theta. A special note here is, I want to emphasize that these formulas apply specifically to externally focusing telescope with an analytic lenses, which eliminates the need for a distance correction term, simplifying the calculation. Let us go through an example now. A tachyometer was set up at a station A and the following readings were obtained on a staff held vertically. Calculate the horizontal distance AB and the reduced level RL of B when the constant of the instruments are 100 and 0.15. So, the readings are given here for you. Let us write down the given data at the first place. The instrument constant K given to you is 100 and C is 0.15. The reduced level of the benchmark is 850.50 meter, and the staff readings at the benchmark are 1.20 meter, 1.90 meter and 2.60 meter, and at B the staff readings are 0.80 meter, 1.60 meter and 2.40 meter. This can be easily visualized from the figure that is given for you. Now, the vertical angles to the benchmark denoted as theta 1 is minus 6 degree 4 minutes for depression, and to B theta 2 is 8 degree 20 minutes for elevation. Let us first understand the readings. The staff readings S1 denotes the bottom hair reading and S2 denotes the middle or the central hair reading, and S3 denotes the top hair reading. So, the staff intercept S is calculated as, so for benchmark capital S1 is equal to S3 minus S1, which is 2.60 meter minus 1.20 meter, that is 1.40 meter. And for the point B, capital S2 is equal to S3 minus S1, which is 2.40 meter minus 0.80 meter, which is 1.60 meter. Now, let us calculate the vertical distance denoted by capital V. Vertical distance V is calculated using the formula V is equal to half K S sin 2 theta plus C sin theta. So, for the benchmark angle theta 1 is minus 6 degree 40 minutes, staff intercept S is 1.40 meter. So, substituting the values, we get V1 is equal to half into 100 into 1.40 sin 0.2 into 6 degree 40 minutes plus 0.15 sine 6 degree 40 minutes, which gives V1 is equal to half into 100 into 1.40 into 0.2319 plus 0.15 into 0.1166. From this we get V1 is equal to 16.143 plus 0.0174. So, V1 is equal to 16.16 meter. Now, for the point B, similar to that of the benchmark problem, we have to proceed the problem. So, angle theta 2 given to you is 8 degree 20 minutes, that is elevation, and the staff intercept S is 1.60 meter. So, substituting the values in the formula, we get V1 is equal to half into 100 into 1.60 sine 2 into 8 degree 20 minutes plus 0.15 sine 8 degree 20 minutes. So, V2 is equal to 1 by 2 into 100 into 1.60 into 0.2869 plus 0.15 into 0.1441, which is again reduced to V2 is equal to 22.952 plus 0.02161, which gives a value 22.96 meter. Now, calculating the horizontal distance capital D. The horizontal distance capital D is given by the formula D is equal to Ks cos square theta plus C cos theta. So, for point B, the angle theta 2 is 8 degree 20 minutes and the staff intercept S is 1.60 meter. So, substituting the values into the formula, we get D2 is equal to 100 into 1.60 into cos square 8 degree 20 minutes plus 0.15 into cos 8 degree 20 minutes, which yields D2 is equal to 100 into 1.60 into 0.9901 square plus 0.15 into 0.9901, which is then simplified to D2 is equal to 156.639 plus 0.148, which gives the value 156.787 meter. Now, calculating the reduced level RL. The formula is reduced level of the instrument axis is reduced level of the instrument axis is equal to reduced level of the benchmark plus H1 plus P1. Substituting the values, we get RL of the instrument axis is equal to 850.50 plus 1.90 plus 16.16, which gives 868.56 meter. Now, finding the RL of the point B. The formula is RL of the B is equal to RL of the instrument axis plus V2 minus H2. So, substituting the values, RL of the B is equal to 850.560 plus 22.996 minus 1.60, which gives 889.926 meter. So, final answer for you is the horizontal distance AB is 156.787 meter and the reduced level of B is 889.926 meter. Now, let us see the types of the telescope fitted in a stereotheodolite. When it comes to telescope in stereotheodolite, there are three main types, that is internal focusing telescope, external focusing telescope and external focusing telescope with an analytic lenses. So, let us first see the internal focusing telescope. This has a focusing mechanism inside. While the distance you measure slightly change the additive constant. It is usually such a tiny difference that you don't need to worry about it. And some modern theodolite fitted with internal focusing telescope is considered as analytic also. Next, we have the external focusing telescope. This type has a focusing done outside the telescope. If your theodolite has this, it is called stadia theodolite. It is easy to use and reliable, but there is an even more precise option. That is where the external focusing telescope with analytic lenses comes in. When you add the special lens, the device will become tachiometer. The good thing about the tachiometer is that it is designed for super accurate distance measurement. The additive constant is usually 0, which means you don't have to adjust for any extra distance. And the multiplying constant is set at 100, making the calculation easier and more reliable. But to make sure a tachiometer works perfectly, there are few things that has to be taken care of. First, the multiplying constant should be exactly 100 to keep any error in the distance measurement very small. That is no more than one error in 1000 measurements. Next, the central hair of the telescope must be right in the middle between the upper and the lower stadia hairs for precise readings. Next, the telescope must have an additive constant of 0 so that the distance calculations are straightforward. Last, the telescope should be powerful enough to zoom in 20 to 30 times and have an aperture, that is a front opening, between 35 to 45 mm to keep the image bright. Now, let us determine the tachyometric constants. The tachyometric constants of stadia theodolites may be determined by one of the methods. That is the determination of the multiplying constant f by I by field measurement and additive constant f plus d by direct measurement along the telescope. At the second, we have determination of both the constants by field measurements. To determine the tachyometric constant of your theodolite, you can follow any one of the two methods. For the first method, start by focusing the telescope on a sharply defined distance object. Once the object is in sharp focus, measure the distance along the top of the telescope from the object lens to the plane where the cross hairs are positioned. The distance is called the focal length and is labeled as small f. Next, measure the distance from the object lens to the vertical axis of the theodolite, which is referred to as small d. The sum of these two measurements gives you the additive constant f plus d. On flat, level ground, measure the different distance capital D1, capital D2 and capital D3 from the location where the instrument is set up. At each of these points, observe the intercepts on the staff held vertically, recording these as small s1, small s2 and small s3. Ensure that the line of sight of the telescope is horizontal by adjusting the vertical circle vernier to read 0. With these measurements, you can use the tachyometric distance formula to create three separate equations. D is equal to f by I s plus f plus d for each cases for D1, D2 and D3. In this formula, f by I is a multiplying constant, s is a staff intercept and f plus d is the additive constant. And solving these three equations will give you the value of f by I. The average of these three values will give you a final multiplying constant. Now the second method. The second method, also known as field method, involves measuring a 100-meter long line on level ground and placing markers every 25 meters along the line. Set up the instrument at one end of the line and make sure it is correctly centered over the ground point. With the telescope horizontal, take readings on the staff held vertically at each marker and note the staff intercept at these points. Substitute these measured distance and staff intercept into the tachymetric distance formula. D is equal to F by I into S plus F plus D. This will result in quadratic equations, and solve these equations in pairs because we have 4 quadratic equations, and determine the values of the tachymetric constants. The average of the obtained values will give you the final values for the constants. Additionally, an analytic lens, which is a special concave lens, is placed between the object lens and the eyepiece of the telescope. This lens is designed to eliminate the additive constant F plus D from the tachymetric distance equation. By doing so, it simplifies the process of calculating distance and heights. If the multiplying constant is set to 100 and the additive constant is set to 0, you can directly calculate the horizontal distance by multiplying the staff intercept by 100. However, there are some drawbacks in using an analytic lens. It absorbs some light which make the image appear dimmer. This lens also increases the cost of manufacturing the telescope. But despite these disadvantages, it significantly simplifies the distance calculation, making it a valuable tool in tachymetric measurements. So, let us close the lecture here. In today's lecture, we covered various important topics related to tachyometry. First, we focused on determining the distance and the elevation formula for inclined sights when the staff is held vertical and the staff held normal. We explored different types of telescope used in the stadia theodolite and examined methods for determining tachymetric constant in the field and through direct measurement. In our next lecture, we will continue our exploration of tachyometry by focusing on tangential methods and solving a good number of example problems to deepen our understanding. Thank you and happy learning.